Hello, everyone. Welcome back to CS4540. This is week 5 video. For this week, we'll be taking a look at 3 videos from 3 Blue, 1 Brown. The first video is going to be visualizing transformers and attention. The second video is going to be attention and transformers visually explained. And the last video will be how might LLMs store facts.
That emerges. So generally try to say, how can I somehow express this notion of letting one thing influencing another, only using the language of multiplying matrices, where those matrices have tunable weights in them that can be, hopefully, learning to do what we want them to do. And there's 3 matrices that are going to come up. They're called the query, the key, and the value matrices. And we'll go through them each one by one. But to set the stage, the query matrix is as if you want to let each word ask a question. So you might imagine the word creature or any other thing in there asking, hey, are there any adjectives sitting in front of me? Because right now it can't really see its context. It just knows its position and it knows that it's a noun. And you also want to give the adjectives that sit in front of it the capacity to somehow, numerically or mathematically, respond to it, answering, yeah, I'm an adjective, I'm in that position. Now, of course, they don't literally ask. Instead, the way that this looks is to associate the embedding for that word in creature with a new vector. It's what we're going to call the that emerges.
Let's talk about how the value matrix helps adjectives and nouns interact in AI models, as explained in this 3 Blue, 1 Brown clip. The value matrix is a key component in attention mechanism. It enables words like fluffy and creature to interact meaningfully. But how does that work? When an adjective is multiplied by the value matrix, it generates a new vector. This vector, when added to the noun's embedding, shifts its meaning in a specific direction. Essentially, this process injects the adjective's meaning into the noun, refining the model's understanding of the phrase. For example, instead of just recognizing creature, the model can process fluffy creature or even fluffy blue creature, making its language understanding more precise and context aware. This mechanism is what allow AI models to capture nuanced word relationships and generate more natural language response.
Attention is something where you would think about those happening all in parallel. And again, the mantra for transformers is that they're very well architected to work on GPUs so that you can run these things in a shorter amount of time, even if it's a greater amount of computation. And what I mean by multiple attention heads here is that this adjective noun example is just one out of many, many different ways that you might imagine context is relevant to updating meanings. You can imagine all sorts of other things, like also in the sphere of grammar, adverbs updating the meanings of verbs, or nouns and their antecedents going together. But it doesn't even necessarily have to be grammatical. Just really anything where you want to somehow transfer information that was in one part of a passage to something that's later such that it's relevant for predicting the next word. That has to somehow happen through these key query and value mechanisms that are asking which things are relevant to which other ones and what changes should take place when that relevance is there. So each one of the heads inside one of these multi-attention
For architectures, particularly transformers, multi-headed attention mechanisms are pivotal. Each attention head within these blocks possess unique key, query, and value matrices. These matrices allow the model to focus on different parts of the input data simultaneously, capturing various aspects of the information. The outputs from these heads are then concatenated and linearly transformed, enabling the model to jointly attend to information from different representation subspaces at different positions. This mechanism is crucial for tasks like language modeling, where understanding context and relationships between words is essential for predicting subsequent words accurately. Understanding these concepts enhance our grasp of how language models process and generate human-like text, contributing to advances in natural language understanding and generation.
consider the phrases American true mole, 1 mole of carbon dioxide, and take a biopsy of the mole. You and I know that the word mole has different meanings in each one of these, based on the context. But after the first step of a transformer, the one that breaks up the text and associates each token with a vector, the vector that's associated with mole would be the same in all 3 of these cases, because this initial token embedding is effectively a lookup table with no reference to the context. It's only in the next step of the transformer that the surrounding embeddings have the chance to pass information into this one. The picture you might have in mind is that there are multiple distinct directions in this embedding space, encoding the multiple distinct meanings of the word mole, and that a well trained attention block calculates what you need to add to the generic embedding to move it to one of these more specific directions as a function of the context. To take another example, consider the embedding of the word tower. This is presumably some very generic, non specific direction in this.
Let's briefly talk about the attention mechanism. As explained in a three blue, one brown clip, the attention mechanism is a key concept in AI that helps models determine which word in a sentence are most relevant when making predictions. Instead of treating all words equally, attention assigns different weights to different words based on their importance in context. For example, the word mole can mean different things: a small animal, a skin blemish, or even a spy, depending on the surrounding words. Attention helps the model focus on the right meaning by computing patterns of influence between words. Originally, word embeddings representations of words in AI models only capture their basic meanings without context. But with attention, these embeddings are updated dynamically, allowing models to understand the relationship between words better. In short, attention is what enables AI to grasp nuanced meanings in language, making modern models like GPT so powerful.
Value map than to the key in query. But in practice, it is much more efficient if instead you make it so that the number of parameters devoted to this value map is the same as the number devoted to the key in the query. This is especially relevant in the setting of running multiple attention heads in parallel. The way this looks is that the value map is factored as a product of two smaller matrices. Conceptually, I would still encourage you to think about the overall linear map, one with inputs and outputs both in this larger embedding space, for example, taking the embedding of blue to this blueness direction that you would add to nouns. It's just that it's broken up into two separate steps. The first matrix on the right here has a smaller number of rows, typically the same size as the key query space. What this means is you can think of it as mapping the large embedding vectors down to a much smaller space. This is not the conventional naming, but I'm going to call this the value down matrix. The second matrix maps from this smaller space back up to the embedding space, producing the vectors that you use to make the actual value map.
Let's break down the concept of queries, keys, and values in attention mechanism, as explained in three blue, one brown's clip. With a multi-headed attention block, each head operates with its own set of key and query matrices. These matrices generate different attention patterns that help the model focus on relevant information. Alongside them, value maps are used to create sequences that contribute to the final word representation. The outputs from these attention heads suggest changes to the embeddings, which are then summed and added to the original input embedding. This process refines the understanding of each word in its given context. Essentially, this mechanism enables the transfer of information from one part of a passage to another. It's crucial for predicting the next words in a sentence by identifying important elements and determining how they should influence the final output. This is the core of how transformers process text so efficiently.
Athletes to their sports. And although a full mechanistic understanding of how facts are stored remains unsolved, they had some interesting partial results, including the very general high level conclusion that the facts seem to live inside a specific part of these networks, known fancifully as the multi layer perceptrons, or MLPs for short. In the last couple of chapters, you and I have been digging into the details behind transformers, the architecture underlying large language models, and also underlying a lot of other modern AI. In the most recent chapter, we were focusing on a piece called attention, and the next step for you and me is to dig into the details of what happens inside these multi-layer perceptrons, which make up the other big portion of the network. The computation here is actually relatively simple, especially when you compare it to attention. It boils down essentially to a pair of matrix multiplications with a simple something in between. However, interpreting what these computations are doing is exceedingly challenging. Our main goal here is to step.
Have you ever wondered how large language models or LLMs seem to remember facts? It turns out these facts aren't stored like a traditional database, but are embedded within the model's parameters. Research suggests that facts are captured in multi-layer perceptrons, MLPs, a part of the neural network responsible for learning relationships between words and concepts. Let's take the example of the statement Michael Jordan plays basketball in the high dimensional space where words are represented as vectors. There exist specific directions corresponding to concepts like first name Michael, last name Jordan, and basketball. When the model processes the input Michael Jordan, the MLP calculates a transformation that guides the representation toward the basketball direction. Essentially, the model predicts what comes next by multiplying word vectors with a learned matrix of parameters. This mechanism enables LLMs to associate related concepts and recall facts based on patterns learned from training data, allowing them to generate responses that seem remarkably knowledgeable.
Associated with one of the tokens from the input text. What's going to happen is that each individual vector from that sequence goes through a short series of operations, we'll unpack them in just a moment, and at the end we'll get another vector with the same dimension. That other vector is going to get added to the original one that flowed in, and that sum is the result flowing out. This sequence of operations is something you apply to every vector in the sequence, associated with every token in the input, and it all happens in parallel. In particular, the vectors don't talk to each other in this step. They're all kind of doing their own thing. And for you and me, that actually makes it a lot simpler, because it means if we understand what happens to just one of the vectors through this block, we effectively understand what happens to all of them. When I say this block is going to encode the fact that Michael Jordan plays basketball, what I mean is that if a vector flows in that encodes first name Michael and last name Jordan, then this sequence of computations will produce something that includes that direction basketball, which is what we'll add on.
Multi-layer perceptrons, or MLPs, are a core part of neural networks responsible for processing and transforming information. Let's break down how they work. The first step involves multiplying the input vector by a large matrix known as W, up, and adding a bias vector, B. This is followed by a nonlinear activation function such as ReLU, which sets negative values to zero while keeping positive values unchanged, similar to how an AND gate works in logic circuits. Next, the transform vector is multiplied again by another matrix. When an additional bias term B, this matrix can be thought of as encoding different directions in the high dimensional space of word embeddings. Finally, the result is added back to the original input vector. For example, if the input vector represents Michael Jordan, these operations might push it towards a basketball direction. This means the final output encodes all three concepts: Michael, Jordan, and basketball. This process helps LLMs refine their understanding of relationships between words, allowing them to recall facts and make meaningful predictions. Okay, thank you everybody for watching this week's video. I'll see you guys in the next video.